enabling true system-level mixed signal emulation. That's right. Emulation is a ubiquitous for qualifying and validating complex silicon systems. It's compromising all over full software stack, driving highly intricate hardware. However, as some of these silicon systems move toward the intelligence edge, the underlying hardware becomes exceedingly mixed signals with the integration of sensors, real-world interfaces, high-speed data converters, but boost regulators, and etc. Traditional emulation techniques only support synthesizable digital logic. As a result, the scope of what can be verified or validated and to what extent is limited. This means that the software-driven, the chip configuration data goes to all the way down to primitive hardware elements or complex calibration loops, and low-power techniques involve the full software stack cannot be fully verified prior to tape-out. This is an absolute necessity in today's complex systems and the cutting-edge manufacturing technology, owing to the cost of unplanned tape-outs and the pressure of delivering the first pass sampled silicon to the customers. The novel techniques presented in this paper focus on removing this limitation and enabling analog mixed signal behavior modeling. The method thereby enabling true and the system-level mixed signal emulation. Introduction. The advent of SoCs that allow basic software stacks on a process cores really changes the validation techniques that rely on the silicon samples for developing a testing software. The increasing the tape-out cost and the pressure of the time to market implied that a software had to be covered with hardware and validated with silicon. Doing so with traditional dynamic simulation-based tools and techniques is highly impractical, and in majority of the cases not feasible given the prohibitive runtimes. However, hardware emulation emerged as the answer to this challenge and become an important part of the verification 2.0 wave. And delivering a speed of several orders of magnitude over traditional simulation. Since then, the emulation has gone through several advanced such as the hybrid emulation and simulation acceleration, advent of the speed bridges for emulating with various Wright interfaces and protocols, and etc. Fast forward to today, silicon systems SoC, chiplet 3.5 and 3D ICs and SIPs and etc. are now even more complicated and programmable than ever, with multiple heterogeneous processing cores running full-fledged operating systems, DSP and AI/ML algorithms. To make matters more interesting, a majority of these also have a considerable mixed signal component to them. As data analytics and processing gets increasingly closer to the intelligence edge. This is true of all end markets and automotive, industrial, communications, healthcare, to name a few. Since the hardware emulation can only support synthesizable digital logic, a lot of features of these complex systems cannot be fully validated with silicon. Further learning as a true AMS or analog mixed signal simulation, where the digital simulator simulated the digital content and analog simulator simulated the analog content, and two simulators synchronized in time using vendor-specific technologies, limit the number of the tests that can be run. This is primarily to do the runtime limitation imposed by the analog simulator. On other approaches such as standard FPU-based emulation, hybrid simulation, and emulation, or representing the floating point real data types via equivalence fixed point bit models, have not been proven to be suspicious or easy to use. These either result in a major hit to the emulation throughput, emulation capacity, or require a major change to well-established analog modeling techniques, such as SystemVerilog, real number modeling, RNM, and the associated digital mixed signals DMS verification methodology. The novel, innovative techniques presented in this paper aim to address to the challenges of enabling true system-level emulation, including synthesis of mixed signal models without a limitation of prior works in this area. The rest of the paper is organized as follows. The next section describes some related work involving the fixed point modeling and explained the downside of such an approach. When they describe the high-level methodology and takes deeper dive into the supported and unsupported construct of the SVLLM, SystemVerilog LLM within the enhanced compiler that handled the RNM in section 3. It will be also include the code example that workarounds as needed so that the simulation and emulation models yield equivalent functionality and accuracy. Section 4 describes the application of these techniques on the basic PLL, as well as a real-life SoC, a 44R transceiver running full-blown the Ubuntu OS on application classes as a multi-core process environment. We will give an example of some RNMs and the compromise of the signal chain and auxiliary analog circuits that constitute this DUT. Next, we will take a deeper dive into the result obtained, including the waveform comparison between the simulation and emulation to illustrate the accuracy. The runtime for each server will be highlighted to show the performance gain achieved. We finally conclude in section 4, representing a summary, our conclusion and future work. Section 2, related work. As cited in the introduction, fixed point bit models have been shown to enable mixed signal emulation but have not been proven to be sufficient or easy to use. An example of this modeling approach was applied to an image sensor. The image sensor shown in the center of the figure 1 was originally modeled using the RNM and executed in the simulation. Those models could be those models could not run directly on a standard FPGA-based and pure purpose-built emulation platform due to their inability to directly process real numbers. Fixed point bit models can replace the real numbers models, but there are multiple factors to consider. One of the most significant is the accuracy versus emulation model size trade-off. The greater the number of bits, the more accurate the model, but that also creates a large emulation footprint. For FPGA-based emulators, if the model grows too large, routing and timing can impact the ability to emulate the model. The purpose-built emulation platform, the size of the emulation model can lead to longer compilation times, affecting the debug turnaround time when used in production verification flow. The fixed point bit models implemented for the image sensor in figure 1 enable the emulation of 5.6 seconds of the real system function in 2.1 hours of emulation time. Of course, there are other commonplace techniques of the transforming a simulation environment to the emulation, like replacing VIP drivers monitors with synthesizable BFMs and replacing memories with their synthesized equivalents, and etc. must be employed in addition to the synthesizable fixed point RNM to realize this gain. However, the key message is the RNM synthesizability is the cornerstone to successfully realize this use case in emulation. This demonstrated the potential potential values of simulation level mixed signal emulation, even though it required months of work to recode the model for emulation and large emulation model size. While the speed is attractive, the engineering cost to create a fixed point model to connect the verification environment to that model to maintain synchronization with the RNM simulation models and validate the overall model accuracy of the overall model accuracy often pre-model accuracy often preclude the development of these models. Any work that can directly make the original RNMs synthesizable without having to recode them would thus be of immense value. Figure 1. Image sensor emulation use case deploying fixed point models in simulation acceleration mode. So, section 3, our approach, solutions, and overall methodology and applications. Our approach to an end-to-end mixed-signal emulation solution is via innovative enhanced to RNM coding guidelines combined with compiler enhancement and subsequent proof of those guidelines with a real-world example. These guidelines were implemented on an emulation hardware platform and the associated front-end compiler to demonstrate the efficiency of the RNMs via execution on emulation hardware. These compilers now support critical RNM features including SV2009 real data types, SV2012 net types, and resolution functions include UDNs such as EENA, delays, floating point operation, basic math operation, and so forth. The compiler output is still mapped to compute elements in hardware, which limited the use of the RNM behavior language features like dynamic arrays and loop limits. However, these are easy to work around without significant issues. As a result of this approach, the overall emulation methodology that the end user is familiar with the relatively unchanged and only requires some additional options and configuration. Below are the examples of some classes of some supported construct and known limitation. This is not exhaustive list. A. Data type support. All standard real data types such as real, short real, real time are supported, along with their unpacked area and struct. SV2012 net types are also fully supported, including resolution functions for multi-driver scenarios. However, the resolution functions must be synthesizable. This means that it cannot use any dynamic arrays, which are quite common. These can easily be replaced with fixed-sized arrays, so the vendor-specific package of commonly used net types are also supported. B. Delay support. Pound, usually sharp, delays are typically not synthesizable. However, due to the ubiquitous usage of such delays in RNM, support for these has been enabled. Statements such as the ones below are fully supported.
always process with time delay and no event. Example, always pound or sharp 10 A assigned from B. Always process with time delay and explicit event. Example, always at A or B begin pound 10 Y assigned from A plus B and the continuous assignment with a single delay. Example, assign Shah or pound 10 Y equal A plus B semicolon. The limitation, rise or fall or off delays specified with a Verilog gated primitive are not supported. These need to be transformed into one of the three constructed above. For example, not Shah write delay, for delay, and 0, O underscore lag is not supported. However, this can be easily transformed into a supported construct as follows. Always add post edge O underscore lag and begin Shah rise delay O temp equal tilt O underscore lag. And always and negate on O underscore lag begin Shah for delay O underscore temp to equal tilt O underscore lag and assign O equal O underscore temp. C. Floating point operations. Math functions and conversion functions operate with the real operand in table 11.1 in the IEEE standard 1817 are supported in DUT except for the inside operator. Majority of the real math functions in table 1220-4 in the IEEE standard 2017 are supported with some minor caveats. Since 20.5 in the IEEE standard 2017 describes the system functions for converting values to and from real number values. $RT or R to I, $I to R, $real to bit, $bit to real, $short real to bit, $bit to short real are all supported. D. DMS connectivity. All industry standard simulators over the year have built various features into their compilers and elaborators to help with the DMS connectivity mismatches between the high connection and low connection and end of any segment in the design hierarchy. These features are typically not part of the SystemVerilog LRM and are commonly referred to as data type coercion and the automatic connection module or interface element insertion. The front-end compiler for the emulation platform has been enhanced to incorporate data type coercion to a great degree. However, it still is not a one-to-one match with the simulator's capabilities. CM insertion is not supported to proactively identify and fix any connection mismatches that would cause issues for emulation build. We developed a VPI and a post-processing Python script to trace every connection from the top level I/O of the design hierarchy to I/O on the leaf instances with the further underlying hierarchy. The VIP pumps the high connections and low connections starting from the top level I/O to I/O at each intermediate hierarchy all the way to the I/O on the leaf cells. The Python script reads all the these high connections and low connections and assembles the signal paths, identifying the signal type, logic, interconnection cost, W real and real variables, and etc. And for every signal in the hierarchy, the signals are then written into an Excel spreadsheet, identifying if there are segments in the hierarchy of the given signal path that might cause a problem during the building the emulation object. Logic, W real, and other custom net types and endpoints are identified vividly. The E, other limitations. All standard limitations of emulation systems related to synthesizability applied unless otherwise stated. Example, delays are typically non-synthesizable but unsupported with this novel methodology as clarified above. In addition, the following constructs that might be important from the RNM and DMS point of view are not supported. Verilog gate primitives and B dynamic arrays and SV construct operating on real data types, concurrent assertions, immediate assertions, coverage, and D force and release operation of the real data types. The 4 test vectors and result. A charge pump phase route loops CP-PLL. A basic of proof of concept, we used a basic charge pump PLL. This is a predominantly analog circuit which is perfect to prove the RNM synthesizability aspect of the enhanced compilers. It also helped us with validating the modeling guidelines, quantifying the changes required, identifying any necessary enhancement to our tools and method. Figure 2 is below is a code snippet from the PLL netlist showing the top level modules for the loop filter and the charge pump C pump. And the loop filter is implemented using the HS implementation of the current controlled voltage source CCVS from the reusable the ADI schematic models library that can take in an array of the ports A_SV and zeros B_SV. These arrays are typically dynamic in nature. However, due to the emulation limitation, we made these static by declaring additional model parameters AP and BP. And the filter itself is implemented as a bilinear transformation with some complex floating point operations. This snippet also shows the use of the real sum data types, which is commonly used in simple UDN. Figure 2 code snippet from the PLL showing top level modules for the loop filter and charge pump C pump. And the figure 3 below shows the top level of the PLL and how the filter, charge pump, shift pump, and modules get connected with the output, the charge pump going to the input of the filter. The main things to notice here is how this connection happens via Wright wire data type, and since the compiler supports the coercion, and so this automatically get as coerced to the appropriate data type, W real sum in this case, at emulation build time. There is no need to explicitly declare this top level signal as W real sum. This might not appear to be a major issue for the smaller example, but would be a huge showstopper for any real-life applications. The snippet also shows the use of the onboard emulator clock. Figure 3 code snippet showing top-level PLL netlist. Figure 4 below shows the comparison of the controller voltage VC, the input to the voltage controlled oscillators VCO, and between the simulation and emulation cases. Assuming the simulation as the reference, the error is less than 0.0423%. Figure 4. Comparison of the CP, PLL, VCO controller voltage between simulation and emulation. The PLL pipe cleaning core exercise helps us to test several pieces of critical required functionality. It uses several net types current modeling and a bilinear transform implementation as part of the loop filters to implement the HS function, which has several complex floating point operations. It also uses the delay, and some of which had been recorded for emulation compatibility. Some of the bilinear transform function also has to be recorded to convert dynamic arrays into fixed size static arrays. Figure 4 is comparison of CP-PLL VCO controller voltage between simulation and emulation. And B, 44R transceiver SoC. Next, we turned our attention to a real-life SoC of 44R ORAN transceiver running a complex Ubuntu OS over complex and highly mixed signal hardware. Current approach with the emulation of this system was to black box the entire analog portion. Selective AMS blocks would be replaced with non-functional, overly simplistic models of just their configuration registers, and the use cases being run on an emulation would simply check the folder resulting the register configuration bits and not the actual real signal output. As for complex calibration loops, there is not really an effective way to verifying these end-to-ends, as they rely on feedback from the analog and appropriate response from the digital, or all the way from the software firmware itself. Baseline digital only emulation setup that we use as a starting point is the simulation acceleration mode, that is, a portion of the UVM test bench, non-synthesizable, runs on the standard CPU-based simulation engine and the entire DUT, as well as synthesizable portion of the test bench run on an emulation platform. A lot of optimizations have been incorporated into this setup over a few generations of the product, ensuring maximum possible speedup and efficiency with the emulation platform. These include well-established techniques such as replacing pure simulation-based verification VIPs with their emulation-friendly equivalent, accelerated VIPs, AVIPs, and optimizing the interface between the simulator and emulator using the performance platform-specific proprietary techniques, optimizing the DUT, build, etc. The first RNM that we white-boxed was the bias generator. All the analog blocks rely on the correct configuration and functioning of this block for this proper operation. The bias generator provided a 50 microampere bias current to the main oscillators on the device. Each core section includes a band gap reference. From this reference, the various bias currents are generated. These can be trimmed, and some currents are constant, others are PTAT, proportional to the absolute temperature. The model, however, does not consider the temperature dependencies. At the trim of the core band gap reference has not been implemented in the new or old models. The model implements a set voltage output which can be brought to the off state by powering down the block. The block contains a comparator which can be used to trim some of the bias currents is relative to the one another. The trimming routine is controlled by a state machine activated in response to a register write. The several modeling techniques are used to produce the overall bias circuit. We have behavior model. These are described next. Category 1, model library. There were several standard components used from the analog devices simulation library. These components have views which can operate across the multiple simulators. These include voltage sources, voltage-controlled voltage sources or gates, and gate competitors, and etc. The necessary subset of the library has been updated to ensure they are emulation compliant. Category 2 is extracted lookup table LUT. The bias currents are generated in direct proportion to an input voltage from the bandgap reference. The ratio between the voltage and current can be trimmed, and such a circuit can be modeled using an extracted lookup table. An internally developed analog devices application was used to extract the LUT and generate the models. The output models types are SUV compatible. This application had been used for previous analog device project. The SP code generated by it required no modification for use with emulation. Category 3, the handwritten SystemVerilog. The use of handwritten models was restricted only to those cases where absolutely needed, such as those where else and if constructs are required to differentiate between the emulation and simulation behavior. Cases where the differentiated requires a simpler behavior for emulation versus simulation to avoid complexity. B manually. It was A, and B is manually managing the signal disciplines, and C, the inserting hand instantiated connected modules. This is an exceedingly small subset of the overall model of the bias generator. Figure 5 is a comparison of some key signals for transceivers bias generators between the simulation and emulation. The bias generator model is automatically now listed from the analog design environment where the level models sit next to their transistor level equivalent circuit. The updated emulation-friendly model was then validated by running the test bench with the transistor level circuit. RNM model in simulation and RNM model in emulation for various use cases, power down, trim, etc. In the emulation case, the test bench runs on the CPU-based simulator and the models runs on the emulator. This is also commonly known as the simulation acceleration mode. Some of the results are shown in figure 5 above. Once all of these were passing, the bias generator was integrated into the transceiver system level duty for a system level emulation run. One of the interesting cases is the bias generator's self-trim routine that is triggered via register writes from the processor's core on the SoC. This allows all key components interacting with each other, software, digital, and analog. The figure 6 below shows the result from the simulation run, and the result from the emulation run are shown in figure 7. The trim routine executes successfully on both. These are differences in output of the constraint randomization solver that result in a way from not being identical. However, this additional capability of incorporating RNMs on the emulation platform comes at cost. the maximum frequency achieved on the emulation platform using full-fledged bias generator RNM drops on from 959 kHz with all digital bias generator to 635 kHz. The 33 degradation. So the 4-hour case, this trade-off being able to synthesizable RNMs in floating point fidelity by sacrificing some emulation speedup is well within bounds of worth it considering all the additional system level mixed signal use cases that can be validated. Pre-silicon. The emulation runtime is 45 seconds versus the pure simulation runtime of 14,400 seconds, thereby yielding a 320 times speedup. We expect the speedup using the emulation platform to be significantly higher as we move to more complicated cases, most of which would be runtime prohibitive on a pure DMS simulation setup. We will also continue working on improving the maximum speed achieved on the emulation platform for mixed signal use cases. The Figure 6 simulation result for a bias generator self-trim routine. Figure 7 emulation result for the bias generator self-trim routine. Section 5, conclusion and future work. Being able to synthesizable RNNs to floating point fidelity on the standard emulation platforms opens immense potential for comprehensive silicon validation of complex mixed signal silicon systems with the entire soft stack at edge. As a basic proof of concept, we use the basic charge pump PLL. This is a predominantly analog circuit which is perfect to prove out the RNM synthesizability aspect of the enhanced compiler. It also helped us validate the modeling guidelines, quantifying the changes required and identifying any necessary enhancement to our tools and method. With a real-life transceiver, we can attest the tools and techniques and methodology outlined this work are ready for the production use with a known limitation that have proven workaround. We can now reliable and truly validate complex mixed signal system per silicon. As part of future work, analog devices will continue to enhance the in-simulation library to be fully emulation compliant. As a result of this, any models created using this library using the boot blocks will be emulation ready without any overhead. From Cadence's point of view, as tools and emulation hardware platforms advanced, there will be more support for additional RNM and DMS construct along with the underlying hardware enhancement as needed. Furthermore, the single RNM code base for simulation and emulation will enable engineers to devote more time to full system verification, driving additional innovation, resulting in higher quality products. The acknowledgement. The authors would like to acknowledge the contribution of various people on teams and Analog Device Incorporation and Cadence Design Systems Incorporation that made this possible. Okay, thank you. Today I led this DVCON2024 paper, the enabling true system level mixed signal emulation. Thank you for your time and see you next time.